Before we get going, feel free to interrupt me at any times if you guys have any questions. I like having a bit more of a dynamic conversation rather than just talking at my webcam for the next hour. So feel free to interrupt, feel free to chat. Let's see if we can get a bit more discussion going. And then you guys aren't staring at my ugly mug for an hour. So today I wanted to talk to you about a Git-like experience for Data Lake. What this is an introduction into what we're calling Project Nesse here at Dremio, and an open source project that I'd like to share with you guys today. So first off, as an outline, I just want to talk to you about the evolution of a data platform, how it's changed since databases basically were first invented. Then we'll take a look at some of the current state and some of the challenges we have in our current state. That'll lead us into how Nesse can help make that better for you. Before we dive too deeply into Nesse, we'll just take a few minutes to run over Apache Iceberg, what it is, how it works, and how table formats work in general. Then we'll take up some use cases, how you can actually use Nesse today, and then finally we'll do a quick demo and take some questions. So with that, let's take a look at the data platform. So we have this big timeline here. I don't really want to go through this completely. What I like to highlight here is that as things have changed and grown and moved on to the cloud and everything else, what we've really seen is two paradigms emerge out of this, two really core paradigms. That's the data lake and the data warehouse. And they're really opposite sides of the same coin. Your data warehouse has it's a lot more structured, a lot more rigid, very opinionated, but it has all of its batteries included. So it's easier to use, it's easier to get started with. And there's a lot of idioms and paradigms and everything else around how to use data in a data warehouse. The downside to it is it's a bit of a monolith. It's hard to use. In some cases, a lot of cases, it's hard to use other tools. It's hard to use it as to pick the best tool for the job. Data lakes, on the other hand, are effectively the complete opposite. It's a bit of a wild west, especially in 2006 when all the data lakes first started coming out, where there's no rules, or there's very few rules, and there's not as many established paradigms. But on the flip side, you can bring any tool you want to the party. So whether that's Dask or Spark or Dremio or Trino or whatever else, you're able to use the best tool for the job for whatever job you have. So out of these two paradigms, what we've seen over the past, say, 20, 25 years is a sort of a convergence of the lake and the warehouse. And what we've seen is the warehouses have slowly become a bit more open. They've moved on to the cloud, and you're able to, say, talk to blob storage, use other tools. So it's become more accepting of some of the data lake ideas. But on the flip side, you've seen the data lake has really changed, has really grown in the past 15 years. First, with things like Hive and adding the idea of a table, so starting to organize your data on your data lake. And then you added SQL interfaces like Trino and, and Dremio. More recently, we've seen the rise of the table transactions and the table formats, which I'll discuss soon. And the idea there is to be able to have some sort of ACID compliance like you have in your data warehouse, but have that on your data lake tables. So now if we look at where the data lake is compared to the data warehouse, excuse me, we're really starting to see only a very few things separating these two. And from the data lake side, the biggest thing there is multi-table transactions, or the traditional transactions you think of in a database: begin transaction, statement, 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 commit. So how can we bring that to the data lake? And then we can really bring these two concepts together. Well, that's where Project Nesse really got its start from. And we sort of saw that not only can we equal the data warehouse in terms of technologies, we can really bring these in terms of sort of technical skill set, I suppose. We can even go further. We can start thinking not just about transactions across the database. We can distribute these transactions across multiple engines. We can start thinking of branches and tags and all this version control. So that's where we're going now. And I think we'll really see, hopefully we'll really see these two paradigms become one, and we can start focusing on one set of tools and one set of paradigms. Before we get into how we think we can do that, let's take a look at some of the problems that are driving the data lake today, some of the things that are really hard to do in the data lake. One thing we can see is if we have multiple mutations across several tables in the data lake. Let's say we have an Airflow DAG or a set of Airflow DAGs, and they're making multiple changes to multiple tables as part of an end-of-day ETL pipeline, for example. Maybe it's something like 3 regions are all committing to the same set of tables to produce up-to-date data sets for the end-of-day data. And we're going to see these things are going to come in, they're going to do a lot of mutations, and there's usually going to be a set of things that have to happen, whether that's building materialized views or creating aggregate tables or these sorts of things. So what happens if our Airflow DAG fails halfway through the DAG? We're going to have some data that's in a consistent state, so that has been updated for today, but some of the data is going to be from yesterday still. So how do we move that? How do we repair that error? Well, we can just run the Airflow DAG again, but in the meantime, our users are going to see 2 different data sets. So one of the common ways we can actually get around this is by creating what we call a pointer view, where we explicitly exclude any data past yesterday's date. And then our downstream users are always going to see the same consistent set of data. And then when we know all of our Airflow DAGs have completed and are okay, we can actually just go ahead and move that pointer. That works okay, and it works, but it's not very extensible. It's not very automated, and it's hard to do this sort of in a long-term strategic way. We also have the problem very closely related to the problem of verification. Let's say our ETL job completes. How do we know that that data is actually correct? And that's the data that our end users want to see. And if it's incorrect, how can we roll back? How can we fix errors? Usually this is going to mean just running the entire ETL pipeline again, because we just don't really know how to back out individual changes or how to fill in individual changes. In the general case, sometimes we can. So how can we think about solving these types of problems? The final problem I wanted to look at is the idea of reproducibility. And I think with the rise of AI and ML, this has become rather important. The idea here is how can we, in very high fidelity, reproduce decisions we've made in the past? Whether that's our individual decisions that an analyst has done, or whether or it's a big ML model that's being run live. So to do that, we typically have to combine some data that's too big to version, some copies of data that hopefully have a lifetime that we can control, and some extra data like analysis and stuff that's maybe stored in Git, maybe it's in a document store. How can we pull all that back and then rerun our analysis on it to know that we'll actually reproduce the answers we produced before, knowing that the data hasn't changed since then? And that's a really hard problem. And I think there's a lot of startups and a lot of open source projects that are starting to look at this and the idea of ML ops, if you will. So those are some of the problems that we have right now. Before I go into how I think Nesse can solve those problems, I wanted to discuss the idea of a table format. So let's take a quick segue into the ideas behind Iceberg. So typically when we're looking at the data on a data lake, we're just going to have a set of files. And those files are things that we're fairly comfortable with already. It's stuff like Parquet or Org or JSON or something. And the idea behind these individual files is they're designed to either read or write or modify single files efficiently. So we can quickly append data to a Avro file, or we can quickly read one column out of a Parquet file. But if we have a very large data set, we have a very large number of files. So how do we do things like organize those into partitions or sensible schemas? How do we ensure that all the files have the same schema? Usually that's something that's done by hand or is done, the query engine might apply a strict schema, but it might not, you never know that this schema is actually going to be followed by all the files in the table. And that brought, that gave rise to the idea of a table format. And the table format here is exactly like the file format, but applied to an entire collection of files. So now we know all these files have the same file format, the same schema, and we're able to efficiently read or write or modify the entire data. set. So things like inserting partitions or doing large operations across the data set, being able to push down SQL statements, these sorts of things. The other thing we want is things to be ACID compliant. And the ACID compliance means we can do transactions and we can have a consistent view of our data set at all times. So the idea of a table format has slowly been evolving. Our Gen 0 here is really just a S3 bucket or an HDFS directory. So we throw a pile of data into the directory and sort of hope for the best. And that's where our engines have to compensate a lot by trying to apply schemas and take a lot of edge cases that reduce efficiency to be able to handle potentially different file formats and schemas. And then when we came around with Gen 1, we have Hive and Hive derivatives like glue, where we're applying a consistent schema. And in some cases, we're able to be ACID compliant. But we really aren't fully bringing to all the possibilities out of our data set. At the end of the day in Hive, you still tend to think a lot about files and partitions rather than the table. And that's where Iceberg and its I wouldn't say competitors, but the similar technologies have led us to. So in Iceberg, when you think about a table, you actually are starting to think about exactly that, a table. Iceberg handles things like inserts and upserts and modifications and changes in schemas and everything else. So it's managing your Parquet files underneath, and you don't have to think about which directory do I have to put this file into to make sure that Hive sees the new partition, for example. And that's a really important innovation towards bringing the data lake and the data warehouse together. So we now have tables and real tables where we insert and we update and we merge and we drop. Now what this also brought around is a full ACID compliance. So we know that we can make changes to our table, we can append data to our table, and the table will always be consistent. The downstream users will never see half appended data or incomplete data. But of course, that's only at the single table level. I'm going to skip this slide today. So how do table formats do that? Well, a very simple way of thinking about this is a table format is effectively a list of files. So in Iceberg, it's actually slightly more hierarchical, and things like Delta Lake, it's actually deltas. But at the end of the day, you're going to look at your data lake, your data lake table, Iceberg or Delta or whatever else, and you're going to get a list of files. And those files are, they may be split up by partition, whatever else. And that's how you read the data. And what happens if you then go ahead and commit or append some data to that table? This is effectively just a transaction. And what's going to happen is you're just going to write a brand new list. And this list is going to have all the new files. So you can see here, list 2 points to 2 of the original Parquet files and 2 new Parquet files, but it no longer points to this old Parquet file. So this is probably some sort of upsert operation. And again, if we perform another transaction, the same thing's going to happen. We're going to write out a new list, which will be a new list of Parquet files. And again, that'll point to the current up-to-date set of Parquet files. And this always happens atomically. And what's interesting is we sort of get time travel or table history for free. So if we want to look at the table as it stood on list 1, say at time t, then we can just read list 1 again. And all the Parquet files from list 1 are still there. We can move backwards and forwards in time and still be able to see all of our data. So we're not really losing anything by making changes to our table here. And what's important is we're able to do this atomically. So list 1 or list 3 is going to be written out, and then anyone who comes along after that is going to be able to read list 3, and that'll be the new up-to-date data. And there never will be an opportunity for a user to read a half-written list 3, for example. So with Iceberg, we can now start thinking about what is Iceberg and Delta and these other tools. We can start thinking about how can we do this at a large scale with multiple transactions. And that brings us to Project Nesse. So Project Nesse at its base is a Git-like experience for your data lake. And when we say Git-like, what we mean is you're able to have concepts like branches, tags, commits, merges. A commit is effectively just a single transaction. In Iceberg, that's the single append or something like that. And our branches and tags have very similar meanings as they would in Git. It isn't, it's Git-like because it isn't Git. It isn't actually Git. We're not using Git under the hood. And it doesn't do things like it's not a distributed data version control like Git is. You also can't do some of the more complicated things that you might be able to do with Git in terms of pulling out of stashes and trying to apply different merges and all that kind of crazy stuff you can get with Git. So it's Git-like, and the idea there is to bring the concepts that developers are familiar with from Git without all of the complexity that Git provides. We've also built this to be cloud native. So this is something that we look at as a potential replacement for Hive, for example. It can run as a function as a service on Lambda, AWS Lambda or something like that. It can run on Docker, Kubernetes. The idea there is it's scale out, it's horizontally scalable. We won't have the bottlenecks like we have in something like Hive. And of course, it's Apache license. It's an OSS open source server and a set of open source libraries. As of today, it already supports a set of common data tools. So we can do Hive tables, Iceberg tables, Delta-like tables, and SQL views. And the idea is to leverage and extend modern table formats rather than trying to reinvent a whole lot of wheels or to try and do a very fine-grained version controller, for example. And aside from what we already support, we're really targeting integration across all major data tools, whether that's ETL or orchestration or eventually data lineage and ML as well. So we're also, with Nesse, you're able to do multi-table transactions. And these are very interesting multi-table transactions. They aren't necessarily the standard begin transaction, statement, commit. You're actually able to do things like cross-table connect transactions across multiple engines. We'll take a look at what that means in a second. And what's interesting here is we're not really doing any data copying. We're not version controlling our data. We're version controlling our metadata. That's a key part here. So the Iceberg manifest, for example, they're version controlled. However, we're not maintaining a copy of every Parquet file that we write. So just to take a little bit more to discuss what Git-like means. First, we talk about a commit. And a commit in Nesse is effectively a transaction. A transaction might be appending data to a table via a single transaction. It could be updating the definition of a view, and it could be on one table or it could be on multiple tables. And in a branch, similar to Git, a branch is a ordered list of commits, effectively. And it has a name, and it's always linear in Nesse. So there's no branches, there's no merge commits, there's no forking of the commit history. There's no merge commits, that sort of stuff. There's only one parent for every commit. And a tag is very similar to a branch, except it's immutable. It points to a particular state and time. So you can think of that as being end of year 2020 or end of day for a particular date. And the idea there is to point to a particular time when we have recorded the entire state of our data lake at that time. And then finally, a merge, very similar to Git. It's a way to move data commits from one branch to another. So we're taking the transactions done on, say, the ETL branch and making it visible to our consumers on the main branch. And that's how we can do, as you'll see in a second, the idea of these multi-engine distributed commits. So let's take a look at a few examples of what this means in action. So before we discussed how to do consistency and verification in the modern data lake, and we saw that there's a few problems with it and it's not very scalable. So what if we were to take that same example as before and apply it using Nesse? So we have as before, we have a Airflow DAG or a set of Airflow DAGs, which are making a series of commits at the end of day. So in step one, we're going to create a branch. We're going to call it ETL. And in step one, anyone who reads from the main branch would be the default case. So end users, BI users, your analysts don't really need to know what Nesse is or what branches are or what Git is. When they come and look at the table, they're just going to see the main branch by default. So while the data engineers are running these big ETL jobs, the end users are still going to come along and see main as it stood in step one. So then in step two, our Airflow DAGs are going to run. They're going to create a series of commits. And each of the dots here is effectively a commit, or as I said before, transaction. And this could be a series of steps being performed by a DAG, or it could be a whole set of DAGs, and there could be any number of these commits. And then at the end of this chain, we can check to look at our data, and we can merge it if we like it. So at this stage, at the end of our ETL job, we can effectively run unit tests or do code review on our data. We can check to see if all the expected data has arrived, if the distribution of that data is correct, all these sorts of things. And if they are, then we can do the merge. And on step three, once that merge happens, any end user will start seeing the new data entirely atomically. So this sort of looks like a transaction. In step one, we're doing begin transaction. In step two, we're doing a series of statements. And in step three, we're doing commits, the commit statement. We could do the rollback statement as well, which would be the equivalent of deleting this branch. And what we get here is something like a traditional database transaction, but with a lot more power. The ETL job doesn't need to be attached to the same database engine or the same database session. Each of these could be coming from different Spark jobs or whatever else. I'd also like to point out for the developers listening how much this looks like a feature branch or developing a new feature on your code base. If you're developing a new feature, you're going to create a branch, and then on the branch, you're going to create a series of commits to add the feature, maybe address some code review, add some unit tests, etc. And then when the feature is complete, you're going to merge the feature back into your main or your master branch. And that's exactly what we're doing here, but we're doing it with data. So as I said before, we're starting to look at these two different types of transactions. We can do a single commit can have multiple statements, so we can do several inserts, so we have a single system transaction, where this is just issuing one commit to your Nesse table, to your Nesse database. And you can also have the idea of these loosely coupled transactions, where you create a branch, you do a set of operations on the branch, and then you merge the branch when you're satisfied with it. And this can be a lot of really large things or small things. You can do schema changes, you can repartition, you can build materialized views or reflections. You can do a lot of different things to start orchestrating an entire set of jobs together without overriding or interfering with what your analysts or end users are doing. Finally, for the use cases, I want to take a look at what the reproducibility use case looks like. So as before, we have an ML model. We want to push that ML model to prod. But we also want to record everything that went into training and analyzing that ML model for posterity to make sure that we are able to reproduce everything. So as I said before, that was sort of a hodgepodge of copied data sets, storing some files here, storing some files there. Where in Nesse, this can be as simple as creating a tag. So in step one, when we push our training run A to production, we create a tag. And then we know if we ever check out the training run A, the data will look exactly as it did when we ran the training run A. So then as time passes in step two, we create some more data, we change some more data, maybe add a few new tables, some new features, this kind of stuff, and we go and retrain the model. So now we have two training runs and two tags. And at this point, we can always go back and look at how we arrived at the data, the ML model for these two training runs. And we can compare these runs, and we can even apply model A to training run B and vice versa. So we can really, similar as you would in an actual Git code base, we can actually go and check out the data as it stood when we actually did these training runs. And we know that that'll be full high fidelity because we have all of the history of our data from when it was originally trained. So now just to take a look at a high-level architecture of what Nesse looks like. So Nesse is running as a daemon, and this daemon is just a REST API, and that's what allows us to have these serverless deployments. So then all of our different downstream connections are, whether that's Hive or Nesse, for Data Lake or for Iceberg, the command line interface or Python client, whatever it is, they all just connect to that REST API. So anything can just connect to the REST API and do what they need to do. The web UI, of course, also connects to the REST API. And then from there, the API is talking to our commit kernel. And that's our version store. This is where the complex Git-like operations actually take place. And that's where a lot of the engineering in Nesse actually took place. And to make this work, we need a backend database to store the history. And right now that's in DynamoDB if you're in the cloud. We have a few other implementations of that and a few more are on the way. And of course, we have our pluggable authorization and authentication. And then we have the idea of these table services. We won't be able to talk too much about table services today, but this is sort of the care and feeding of your data lake. So one of the most important things there is garbage collection, which is cleaning up data after it's no longer referenced in Nesse, or compacting data. So we always have the small file problem when working with data sets, where we have 1,000 Parquet files of 100 kilobytes each. And a table service is something that can go on and automatically compact all those files into correctly optimized sized files. And that can be done online behind the scenes without actually your end users noticing. And with history, so you can even go back to before it was compacted if you so choose. So just to take a brief look at what the current status of Nesse is. So we have a Docker image and AWS Lambda image. You can use those today. You can directly access this through PyNesse or the CLI, which is built on our Python client. There's a Java client UI. And then the Java client is leveraged by Iceberg, by Delta Lake, and by Hive to directly communicate with Nesse. We've really put a lot of work into making this high performance, so we're able to do several hundred commits a second, several hundred operations per second, which is really, really powerful if you have a very big database with a number of transactions happening at the same time. And then finally, as I mentioned, we have a variety of storage backends. The best use case right now is with DynamoDB, but you can use a number of other ones. And then future work, we want to improve our interaction with Hive. There's going to be a lot more work happening in Iceberg. We're big fans of Iceberg, so we really want to make sure that that's a really high quality integration. Some more work happening in Delta Lake, tons more integrations across the spectrum of data tools, and of course those table management services that I discussed. So all these things will be coming out, in the next months to year. So very active project right now. I hope you'll see a lot of new changes coming. And with that, I'd like to do a demo. So I'll exit this. I'll move over to our Google Colab book. Hope everyone can see this and it's well sized. So what I want to do here is I just want to do a simple demo of how Nesse works in real life. So to do that, I have a Nesse server running, a Spark instance running, and then some data has been downloaded in this PySpark Colab book. And you can access this Colab book online, and anyone can run this, and you can even follow along if you so choose. So I've already run these two commands, and what this has done is pulled down our data, set up our environment, given us a Spark context, that sort of stuff. So let's move on to the interesting stuff. First, what I want to do is I want to go and I just want to create a branch. And at this stage, we're going to run the Nesse command line interface to create the branch dev. And this branch dev will be created at the same place in history as main by default. And we're just going to grab a Spark session that's referencing that branch as well. So now if we take a look at all of our branches, we're going to see we have two branches, main and dev, and you can see they're both pointing to the same commit hash. And this is as we expect, we just created the branch dev to point at main. So at this stage, we have two branches and one empty commit. So now we want to do, like we discussed before, we want to do some work on our dev branch. And this is going to be a series of commits to add some tables, to modify some tables, and it will merge that all back into main. So what we're going to do here, you can see we're going to take the Spark context for dev, and we're just going to create two tables, and we're going to read some data in to those tables and write them out as Iceberg tables. And they're going to be located in the Nesse catalog at the NBA namespace, and the tables are going to be salaries and total stats. And these two very simple operations are just going to, as I said, read in these CSV files and write them out as Iceberg tables. And at this stage, here and here, we're going to actually create two commits. So one commit is going to create the empty table, and another commit is going to fill data into the table. And similarly for the second table. So we've now gone and created four individual commits on the dev branch. So now if we use our original Spark SQL or Spark context and we do a select from the salaries table, but we do it at the dev branch, we'll be able to see the salaries table as it stands on the dev branch. So take a look at that now and we'll see it on the dev branch. And if we were to run this without the dev branch, we would see an error because there is no dev branch, or there is no salaries table in the main branch. So now we can check to look at our contents, and you'll see that there are no tables in the main branch like we expect. And on the dev branch, we have our two tables that we just created, and they're Iceberg tables as we expect. And then finally, we can take a look at our two branches, and we can see that the dev branch has a different hash as the main branch. So as expected, our dev branch and our main branch have diverged. So now we can just go straight away, and now we've taken a look at our data. We're happy with how the data looks. We've added these two tables. We now want to make them available to end users on the main branch. So we're going to go ahead and do that merge. And here we're merging the dev branch into the main branch. And when that's complete, we can take a look at our branches, and we'll see that they're, as expected, both on the same commit. So now we want to do the same thing again, but now we're going to do a bit more. We're going to append some data. We're going to create a new table. We're going to change the schema of another table. So again, we're going to create the ETL branch. It's going to be based off of main. We'll get our Spark session for that. So now we can see we're just inserting data into salaries for some new data here from this data frame. So now the first operation here is to just add data to a table. And this you can think of as similar to our example before, where we're going to run some ETL jobs, and the end users are still able to see what's on main, but we're able to do a number of things to the ETL branch without them particularly noticing or even caring. We can do some more expensive things. We can say drop an entire column, or we can create a new table and add some data into it. And again, when we look at this after it's run, we can see that on the ETL branch, we have this new table. If we were to look at it on the main branch, it wouldn't exist, similar to before. We can take a look. We can look at what's on main. And again, there's two tables that we merged in the previous branch. And if we look at what's on ETL, we'll see that there's three tables. And again, we can go ahead and merge those things. And now we expect our main and ETL branch are on the same hash, because one has just been merged into the other, and the dev branch has now fallen behind. And at this point, the dev branch really isn't useful for us. We actually probably want to go and drop the dev branch in a production system. So finally, I want to show the idea of being able to do an experiment. Let's say that you have a complicated SQL query that you want to optimize. And you think that you might be able to optimize it by changing some schemas or getting rid of data, maybe trying out a new partition scheme. So you can go and make all these changes to your branch, to the experiment branch, and you can test. So you go and run those queries. You can see if those queries are faster. And if they are, you can go ahead and merge it. And if not, you can just throw out the experiment. It's not a problem. So again, we're going to drop this table. We're going to add some more rows, and we're going to, again, just take a look at our experiment branch. And again, that's only the 2 tables because we dropped one above. And on the main branch, we have all 3. So now we can go and take a look at our data. We can see that salaries on our experiment branch has 58 rows, and salaries on our main branch has 54 rows. This is as expected because above we added those 4 rows to the data set. So now we can take a look at this data. We can decide, do we want to keep this? Do we want to merge this? Or if it's the experiment branch and the experiment hasn't panned out, we can just go ahead and delete the branch. And we know that after the branch is deleted, that will that the data that we created on the experiment branch will eventually get garbage collected and removed. We never have to think about it again. So that's the demo. With that, I'd like to thank everyone for coming. Here's some links if you want to get started with Project Nesse. It's an open source community with a very new open source community. We're actively seeking contributors and people to work with us on the project. So if you're interested, give us a shout. Thanks very much.
Great. Thanks, Ryan, for the presentations. So now we are open up for the Q&A. I see we have a few questions in the chat. Just quickly remind everyone, it's times for the Q&A time. If I have any questions, please post in the chat. I know, again, select to everyone so we can see the messages. Also, if you prefer to speak, ask questions, feel free to raise your hand. You can speak to ask questions or even make any comments. So hi, Ryan. I see there are a few questions in the chat. You can go through from the top, or if you want, I can read it to you too.
Yeah, if you wouldn't mind reading, I'm having trouble finding the chat window.
Okay, yeah,
Sorry.
The chat is somewhere. Okay, I can read to you. I think the first one, Luke, he asked, he kind of comments if, he see a lot of requests out in the wild for good data versioning tool, alternative to DVC, I believe, and see if Nesse fits, the pictures.
Yeah, I've never actually used DVC very much. I think DVC is more geared towards a sort of a complete data, so you can version control images and all kinds of large data sets. I think that Nesse is really more focused on Iceberg tables, Delta Lake tables, some of the modern analytics tables formats rather than a broad set of machine learning data.
Another question from Peter. He's asking, is it distributed like a Git? I think the other one comments it's not. Maybe you can, if you want to comment on asking if it is distributed.
Yeah, I think the problem with distributed is it implies you'd have to pull your entire data set to your local machine. So one of the reasons it isn't distributed is you're only having one copy of this data that's on your data lake, whether it's the S3 bucket or whatever else. It's not really feasible to clone that S3 bucket. So it doesn't really make sense then to make the backend distributed either, in the same sense that Git is, of course.
Another question is, if a branch merges to the main branch, how it works to rebase another branch? Do you need to manually to run all of the operations again?
I guess that's sort of a merge conflict at that point, right? Is that what you mean?
I'm not sure this one is actually. Hi, Kevin, if you later on maybe you want to clarify a little bit on the questions.
So I think the idea behind, so if I were to have branch A that's been branched off of main, and then I merge data into main, if you wanted to rebase A, you can just rebase that. That would effectively replay those commits, but it wouldn't actually redo all the actions. You would just get the new manifests. If there's a commit where a commit is defined as one table has changed on both branches, then you have to kind of fall back to your underlying table format and redo those operations to make sure that you can actually merge those things correctly. You can imagine if you added a column with the same name in two different branches, you'd have to actually drop down to the iceberg or the delta-like table and really by hand figure out what happened and how to fix it.
Great. Next question from Michael. He asked, perhaps you will demo this, but how do you handle conflicts? A master has the same table with different data or different updated rows, or does the merge just override it?
Yeah, as I was saying, the merge would, you'd have to solve that in the underlying table format. And I think the idea there is it's sort of like Git. If you have a merge conflict in Git, Git's going to say that that file needs merging. And then you look at the file in your diff editor to pick which of the two you want to do. It's the same story with Nesse, but it's just a bit more potentially expensive because you have to go into your underlying Iceberg or Delta-like files and go ahead and rerun those operations, whether that's an append or a merge or something like that.
Great. I see another one is more kind of comments. Say from Edward, it's great presentations. He's suggesting have hosting more, or this more kind of to AI camp for us to host more such events on Spark, PySpark, or Spark SQL related to the data lakes and data operation technologies. Another one is, I guess you're going to share the slides, the links, and also the node, the demo you demoed. It's one of the link on the slides or somewhere.
Yeah, all these links are clickable, but obviously you can't click them because it's my presentation. I'll send this around. I'll send it to you, Bill, and then you can pass it around to the.
Yes, yeah, absolutely. Yeah, you can just send to me. I will share to our attendees.
Yep.
We have a few more minutes left. Anybody have more questions? Again, feel free to type in the chat. And I mean, if you prefer to speak, you can actually right now, you can just unmute yourself to speak if you want. Thanks, Todd, Paul, for Raw for the comments.
I see that any prerequisites to run Nesse. No, you can just run the Docker image anywhere. The only thing you need is a version store. So DynamoDB is the best one, but we also support an in-memory one for testing, and there's MongoDB, RocksDB, and SQL backend on the go. So those should be ready in the next few months. And I'll send the Google Colab Jupyter Notebook out. You can just copy it into the, so everyone should be able to access that.
Yeah, great. Yeah, if you can just copy to the chat, it should be easier for everyone to grab it right now.
We've looked at Redis. I see someone just asked about Redis. We haven't planned on supporting Redis yet, mostly because of the, I don't really know how to solve the durability. So if Redis crashes before it dumps to disk, then we could potentially lose commits. I know there's a few different ways to make sure that Redis always writes to disk and stuff, but we just haven't experimented enough to know if Redis is a good solution there. It'd certainly be faster for certain types of commits than Dynamo, but it's something we have to investigate still.
All right, any last minute questions? Thanks, Joseph, for the comments.